Okay, guys. So to create VT graphs, we just graph the data from the problem, just like we did on DT graphs. Only once we've created our graph, what we have graphed means something different. Okay. So problem 1 says, draw a graph of the motion described. A blue dog accelerated from 0 to 8 meters per second in 8 seconds. And it continued this for 4 seconds. So 0 to 8 in 8 seconds. So I grab my line, and this one I've already done for you. I grab my line. I go from 0 to 8. Okay. That is 0 to 8 meters per second. So this is the speed that the dog sped up to. Okay. And it did that over 1, 2, 3, 4, 5, 6, 7, 8 seconds. Once it had done that, it continued this speed, the same speed of 8. It did that for 1, 2, 3, 4 seconds. And so that's our graph of that motion. All right. So what we can see here is the dog sped up, and then he kept that constant speed, constant velocity. Okay. Problem number 2. A brown cat sits on the windowsill for 5 seconds before running away 5 meters per second for 3 seconds. So he's sitting still, right? He does that for, what does it say? 5 seconds. So we're going to do sitting still. On a VT graph, sitting still is going to be a velocity of 0. So we get down here, we have the cat sitting still for 5 seconds. It's got a velocity of 0. 1, 2, 3, 4, 5. Okay, and it'll actually be right on this line. I'm going to put it a little above it just so we could see it, but technically it would be even lower. Okay. All right. It should be a little lower than that. That's good. So he's got 0 velocity for 5 seconds. Then he runs away at 5 meters per second for 3 seconds. So somehow the cat runs away at 5 meters per second. 1, 2, 3. There we go, for 3 seconds. Well, the cat can't just suddenly and automatically take this speed. So we know that we're probably going to need a line. And if you skip this part, it's totally understandable. We need a line to connect this. This is the very short period of time that the cat actually sped up. And I could tell you, the cats are funny animals in that they're able to speed up. They're able to accelerate just about that much. I think Mr. Wayne would pretty much agree with me. They can suddenly be going 5 meters per second.
Yeah, if you clap when my cat's not looking, it will accelerate in the upward direction at about that speed.
Yeah. Yeah, cats are unlike anything else in physics. They can actually accelerate instantaneously like that over almost no
Except
time.
for electrons.
Also electrons. We're not going to get into metaphysics right now.
So they're made out of electrons, but also they're a liquid because they take the shape of any container that they're in.
Yeah, I don't know. I don't think so. We're not going to get into that right now. All right. Our next problem, we've got 2 balls. We've got a red one and a green one. Okay. And one accelerates 3 for 4 seconds. The other accelerates 1 for 12 seconds. So we're just going to basically plot that. So 3 meters per second for 4 seconds. Actually, this should be 3 meters per second squared. Sorry. 3 meters per second. For 4 seconds, it did this. And then it did this. And then it did this. For 4 seconds. It did that over 4 seconds. Okay. Sorry about that. That is format. Next. Superscript. Sorry, guys. It means a totally different thing now. Okay. It did that for 4 seconds, and the green ball did 1 meter per second squared for 12 seconds. So every time it went 1 meter per second faster, it took 1 more second, and it did this for 12 seconds. Okay. So which ball rolled faster? Well, it's a trick question. Both of these balls ended up with a velocity of 12 meters per second. It's just that the green ball got to that speed much earlier. We could see that here. It's a good guess. It's a good guess, the red one, but we can see it took more time for the red ball to get to that speed. Okay. I apologize for the sloppy question there. I did put that together in a hurry, but hopefully that clears that up. 3 meters per second squared for 4 seconds, accelerated 1 meter per second squared for 12 seconds. Okay. On the next slide, a red dirt bike, a velocity of 12 meters per second. Okay. So we're just going to start 12 meters per second. Put this line up here. Over 4 seconds, he slowed to 0. Move these out of the way really quick. Over 4 seconds, he slowed to 0. So 1, 2, 3, 4 seconds, he got down to 0. Bam. Okay. He slowed way down. He then accelerated to 10 meters per second in just 2 seconds. So he got up to 10 meters per second, but it took him 2 seconds. So this is a graph of the motion of the dirt bike. He slowed way down, and then he zipped and sped way up. This third line is not useful. This next slide, we've got a green car and a brown hare. I'm sorry, this was supposed to say car. A green car and a brown car. Okay. 6 meters per second in 6 seconds. Okay. Move these out of the way. 6 meters per second in 6 seconds. Move these out of the way. So he got up to 6, and it took him 6 seconds. Okay. Then decelerated 6 meters per second, and it took 6 seconds. So the same thing, but downward. Okay. So 1, 2, 3, 4, 5, 6 seconds. And it goes down 1, 2, 3, 4, 5, 6 meters per second. Okay. And that was supposed to be the green car. So, oops. That's all right. I'll just recolor these. Okay. The brown car accelerated 8 meters per second for 3 seconds. To 8 meters per second, and it took it 3 seconds. So 8 meters per second. There's 1 second, 2 seconds, 3 seconds. Okay. Okay. And then it said that it then decelerated to 0 meters per second in 1 second. Okay. Move these so that I can grab them. 0 meters per second. And it did that in 1 second. So just bam, like that. Okay. It then accelerated to 7 meters per second in 1 more second. So this is This is not likely to actually happen. Okay, we're just playing with some physics graphs here, but this is what happens when a teenager drives. You slow down very quickly and you speed up very quickly, 7 meters per second in 1 second. And then these two lines, of course, are not needed. Okay, this is a car speeding way up and then slowing way down and then speeding way up again, which is exactly what it's like when a 16-year-old drives. Did anyone have any questions on how to graph any of this motion? Okay. All right, I'm going to go ahead and post this video. I think it's going to be useful for us to go over this stuff. If at any point you need to go back and pause any of this and look at the motion, feel free.